Public Economics, Chapter 6.35, Pay-as-you-go Pensions and Economic Growth, from the book Public Economics, the Macroeconomic Perspective. In the last video, we looked at the effect of elastic labor supply on the welfare and equilibrium effects of a pay-as-you-go pension system, and we analyzed the distortion that is inflicted upon our labor supply decision if there are labor income taxes, social security taxes in order to finance pensions of the current retirees. Now we go one step further and integrate growth. Economic growth is important because it drives the rate of return of the public pension system. So look at present public pension system like in the United States or in Germany or Japan. What they do is they take contributions from the workers, usually levied upon the labor income on earnings, and transfer them to the current old. Now the rate of return on your contribution to this pay-as-you-go pension system depends on the economic growth rate. So if you, for example, pay contributions today and retire, let's say 20, 30 years, well, the workers in 20 or 30 years then pay for your pension. And of course, if we have economic growth, their wage income will be much higher and you will get a higher pension. Ergo, your rate of return on your investment in the pay-as-you-go public pension system increases. And we would like to get an estimate of the quantitative effect of this economic growth and also conclude by telling you how it affects the optimal public pension system at the end of this lecture. So let's get into the slides of Chapter 6 on Chapter 6.35, Public Pensions and Economic Growth. Okay, so let's get to page, if I remember correctly, 57, yes, where we start with this chapter. So we introduce public pensions, economic growth, as we did in Chapter 3 on the overlapping generation model. So if you remember there, we introduced economic growth as labor augmenting technological progress, AT, which simply increases productivity of the factor labor. And our labor here is the number of workers, NT, times the hours they work, LT. And the factor AT grows at the rate gamma. Now we could have introduced technology growth here also as capital augmenting and total factor productivity because it doesn't really matter with Cobb-Douglas. But if we assume a substitution elasticity different from one, then we know that the only way to specify economic growth, technological progress, is by labor augmenting technological progress. We set the growth rate equal to 80%. Remember that we look at a 30-period horizon. So each period, when we're young, we work 30 years, and when we are tired, we live for another 30 years. Well, this amounts to approximately an annual growth rate of 2%, which we observe more or less in the United States. So our lifetime utility is unchanged. So we use equation 16. And lifetime utility is additively separable in consumption today, utility from consumption today, and C1t, and next period, ln C2t plus 1. So we use logarithmic utility. We discount utility in the next period, in period t plus 1, by the factor beta. And the superscript 1 and 2 denote the age. So 1 is the young household, the worker. 2 is the old household, the retiree. And we assume an additive term in the disutility from labor, where, as you remember from the last video, nu1 denotes the fresh labor supply elasticity. So by how much Labor supply increases if the net wage increases by 1%. The budget constraints are familiar to you from the chapter 3. So WT denotes the wage per efficiency unit, and we work efficient units AT, LT each households. We can also interpret WTAT, the product of these two variables, as the wage per hour. So WTAT times the number we work, LT, is our wage income. And we notice that the wage rate per hour per time unit grows at the exogenous rate gamma of the labor augmenting technological progress. Our labor income, our earnings, are taxed at rate tau, which is our social security tax. From our labor income, we subtract consumption to get to our savings ST. Next period consumption when retired, C2T plus 1 is equal to our savings ST plus interest on savings RT plus 1 ST plus our pension income in old age. And we denote the pension income by PEN, P-E-N. So when we substitute savings from equation 35b in our consumption savings in 37a, we get to 37c, our lifetime budget constraint, so that the present value of consumption expenditures, the left-hand side of the equation 37c, is equal to our lifetime income, which is net in earnings this period and discounted pension income in old age in period T plus 1. And we can, of course, as we did before, just derive the first order condition, which imply the Euler equation 38a. So how we should spend income in period T. Should we consume a marginal utility here, an extra unit of income, and consume C1T, or should we save it and consume the savings plus the interest rate next period? And we are indifferent between the uses of the marginal income here if equation 38a, the Euler equation, holds. 38b is the well-known first order condition with respect to labor. So on the left-hand side, we have the marginal disutility when working an extra hour. And on the right-hand side, we have the utility gain of having an extra unit of income. Now, in our model with economic growth, the individual consumption grows at the rate gamma. And we have to translate it into stationary variables by dividing it by AT. If not, we cannot solve our, for example, steady state system, our systems of equations in steady state, because the variables would be growing over time. So if we divide individual variables C1, C2 by AT, we can transform the first order condition 38 into the stationary first order conditions 39. And substituting 39a into the lifetime budget implies stationary savings, again expressed as stationary variables by dividing savings by AT, and also defining stationary pensions in the same way. Next, we have to consider the condition that the social security budget is balanced. So total expenditures on pensions in period T plus 1 are equal to total revenues generated in period T plus 1. We could have also specified it as a balanced budget in period T. Notice that the number of old people in period T plus 1 is equal to the number of young people in period T, NT. and that the number of workers in period t plus 1 who contribute to the social security system are equal to nt plus 1. And by dividing through nt, we get the stationary social security budget equation 40. The firms maximize profits, and we know this profit optimization calculus from chapter 3. And the wage rate is equal to the marginal product of labor and the interest rate equal to the marginal product of capital, where we have defined lowercase k as the capital stock per effective labor, per effective worker. So we divide the capital stock, uppercase K, aggregate capital stock, by the product of labor productivity A and the number of workers N. To close the model, we look at the capital market equilibrium, where aggregate savings at the end of period T, NTST, are equal to the beginning of next period capital stock KT plus 1, and by transforming this capital market equilibrium condition into stationary values by dividing by AT/NT, we derive equation 42, which is our equilibrium condition, capital market equilibrium condition in stationary variables. Tilde ST, the savings in period T, are equal to KT plus 1 times 1 plus gamma times 1 plus N. And we have derived the stationary savings tilde ST at the right-hand side of the equation 42 above. Now this equation still contains the factor prices WT, the stationary wage rate, and RT plus 1, the interest rate in period T plus 1. And we can substitute from our factor prices 41A and B, our marginal products, into this equation, and then we again have derived an equation just in the variable KT, which we can solve with the nonlinear equation solver. So let me summarize our equations, our 7 equations that characterize our equilibrium here. Equation A is our Euler condition, equation B our first order condition with respect to the optimal labor supply. C and D are the factor prices of wage rate and interest rate. Equation 43E is our capital market equilibrium. F is our balanced budget of the Social Security Authority, and G is our lifetime utility. Again, by the law of Weil-Rah, we do not need the resource constraint. It is implied by the other constraints of the economy, by the capital market equilibrium, the balanced budget of the Social Security, and the lifetime budget. We calibrate the model as before, and let us look into the MATLAB program to see how we solve this. So for this reason, please load the program Chapter 6 Social Security 4.m into your editor. The same holds for Gauss, so it's really pretty much the same. That's why I just demonstrate this program in the MATLAB editor. And of course, first, what you should always do when you have loaded the program into the editor, see if it works. So just run the program, and you're asked to press the key. We have introduced a couple of pause statement or wait statements in the Gauss program. And here you find the optimal solutions, the calibrated parameter μ0, and the accuracy of the final solution. And this program also computes the consumption equivalent change, the Wellforce change. So let me briefly describe what we do in this model. We just saw the 7 equations in the steady state. And you also find this in the function or procedure in the Gauss program. And the 7 nonlinear equations that we just saw are presented here by the 7 equations y of 1 through y of 7. And we just solve a nonlinear equation system. So this particular program is really easy, and I do not get into much detail. Since, however, we have a new program, a new model, a new environment with growth, we have to recalibrate the model. So our steady state system here is an endogenous equation system in the variables k, l, w, r, c1, c2, and the pensions, which I have denominated in this program here by d. Now, in order to calibrate the parameter nu0, which stems from the utility function of labor supply, we set labor supply equal to 0.3. So we demand an equilibrium steady state labor supply in the initial steady state in the benchmark of 30% of your available time. And nu0 becomes the new endogenous variable. And this is implied in the function or procedure calib nu0. So here you can see that the variable L has been replaced by the variable nu0, where we recalibrate the parameter nu0, which measures the weight of this utility from labor. And we find it's very close to the value that we used before, 257. So the first 3 digits are the same. Otherwise, we just use the same values that we used before. So we use the same value for beta, for alpha. The only new values are gamma, which is now 0.8, the economic growth rate, and nu0 has been recalibrated so that the benchmark equilibrium supply, labor supply, is equal to 0.3. We also used the same Frisch elasticity, which we set to 0.3. And the results are presented in, and the results are presented in the following table, which is table 6.4 in the book. So on the left-hand side, here in the first entry column, we have the case that social security contributions are 0. So we study the case without pensions as our benchmark case. In this case, we calibrate nu0 so that the labor supply is equal to 0.300. So we supply 30% of our available time, which is normalized to 1. Our capital stock here, which is capital over A times N, is equal to 0.00725. Our production is equal to 0.0786, again expressed as production per A times N effective worker. And of the consumption equivalent change, the welfare effect of changing it to tau equal to 0, of course, is equal to 0. This is our benchmark case. And now we consider the same exercise that we did in the last video, in the last chapter. We introduce a pension system with a social security contribution rate of 30%, so something like a social security system that we observe in Southern Europe. And in this case, the reduction of the capital stock savings fall by more than 60%, just like in the case without growth. We also observe that the labor supply is distorted by this extra tax on labor supply, by this extra wedge that's introduced by social security contributions. So the labor supply falls by approximately 2% again. And output, the fall in output, is pretty much the same as in the case of without growth. Now, the welfare effects amount to 37% of total production. So now we cannot compare the effects of a change in the social security system to our old benchmark without growth, but of course we have to compare it with the case where we have economic growth but no pension case. So we compute the consumption equivalent change just like in the case before, and it amounts to 37%. So it's a little lower than without economic growth, and that's small wonder because, as we have argued in the beginning of this video, if we have economic growth, it increases the rate of return of the pay-as-you-go pension system. The higher the growth, the higher is the return that I will get from the pension system, because in 20, 30 years, when I am retiree, you will earn much more than I do today, and your contributions will affect my pensions. And in the program chapter 6, Social Security 4.m or G, depending on whether you use MATLAB or Gauss code, we derive this consumption equivalent change. And of course, you can download this computer code from my homepage. So we have noticed that the introduction of economic growth reduces the welfare effects a little bit, and also the equilibrium effects here, but the change is very small. So let's keep this in mind by concluding this video looking at the sensitivity of our welfare losses due to public pension with respect to the parameters that you got to know. In the problem 6.1, I ask you to compute the sensitivity with respect to the intertemporal elasticity of substitution of our results, or equally with regard to the coefficient of relative risk aversion, sigma. There you found that with higher risk aversion, our welfare losses go up. So here in our model, looking at the Euler condition 43a, we have assumed log utility. So therefore, we effectively have imposed a relative risk aversion coefficient equal to 1. If the risk aversion sigma goes up, well, then how does the Euler equation changes? The sigma enters these equations here as the exponents of C2 and C1 respectively. And you will find that if we increase this risk aversion or decrease the intertemporal substitution elasticity, our welfare losses will go up. We also introduced the Frisch labor supply elasticity. So where do we find this parameter? It enters our equation on the optimal labor supply, our first order condition with respect to labor. And nu1 is our Frisch labor supply elasticity. And of course, it's straightforward to understand that with higher Frisch labor supply elasticity, labor supply decreases and the distortion from public pensions increases. So with regard to the Frisch labor supply elasticity, nu1, the effect is also straightforward. The higher the labor supply elasticity nu1, the higher will be the welfare loss. And we have looked at the case nu1 equal to 0.3. This is at the lower boundary of values estimated empirically and applied to macroeconomic research in dynamic general equilibrium. So our distortions and our welfare losses are higher, should be higher, using, let's say, a midpoint or the upper values in the upper range of the empirical estimates. We have shown that the economic growth rate gamma, the higher the economic growth rate gamma, the lower is the welfare loss. And we have already argued that the rate of return from the public pension system, from a pay-as-you-go system, or of course depends on the population growth rate. If there's high population growth rate, more workers will pay for my pensions in 20 years, and of course This means a higher pension and therefore a higher rate of return on my contributions to the public pension system today. So as a consequence, with higher population growth rate, the welfare losses will decline. And vice versa, in our model, we have not considered so far life expectancy. So people lived 60 years in our model, both periods, period T and period T plus 1. And at the end of old age, in age 2, at the end of period T plus 1, we die for sure. Now, this is, of course, not the real life. Life expectancy increases in most countries, with very few exceptions. So, for example, in the United States, I think it was last year, 2019, where life expectancy actually decreased a little bit, but usually it increases over time, and it will so for the next 30 years, according to projections of the United Nations. So if life expectancy increases, of course, it means that the cohorts of the retirees will increase, and this will decrease the rate of return from our pay-as-you-go pension system, and therefore welfare losses will increase with higher life expectancy. Now, these 5 sensitivities here, these 5 parameters will be important for the study of optimal pensions. And let me also give you a preview of what we will do in the following chapters. So we look at optimal pensions, we look at pay-as-you-go pension system, and we will look at a much more sophisticated model. So we will introduce annual periods, we will study the survival probabilities and life expectancy much closer than we can do in our simple 2-period model. And then we will in particular also introduce income uncertainty. Some people are lucky and earn a lot during lifetime, some people are not. And all these factors are important to derive the optimal amount of pensions. And we will find that pensions, of course, should be highly progressive, so that basically people in old age receive more or less the same pension, and we redistribute in old age from the rich guys to the who have contributed a lot to the pension system to those who have contributed little to the pension system. Given this schedule, that it's rather lump sum and rather progressive, as we call it, the optimal amount of public pension is found to be really low. So it's usually in the range of 0 to 20%, and on average it's around 10-15%. And our 5 parameters here that we have emphasized in this list here also affect the result of optimal pension system. So if we have a high coefficient of relative risk aversion, as we have seen, the welfare loss from public pension goes up. Therefore, when we have this more sophisticated large-scale OLG model, we find that with very high risk aversion, let's say 4 or 5, it's optimal to basically abolish public pensions. Similarly, a higher fish labor supply elasticity nu 1 drives up the cost of public pensions, and the optimal pension replacement rate, so the ratio of pensions with respect to pre-retirement earnings, should also go down to 0. Economic growth is very important. So if we have no economic growth, then the optimal pension system is basically 0 replacement rate, no pensions. Population growth rate is also important. So with higher population growth, let's say like in the 60s, the pension system, the optimal replacement rate is much higher than today. In fact, if we consider the year 2020, in our benchmark case, we will find that the optimal pension system has a replacement rate of 10%. So pensions should be about 10% relative to pre-retirement earnings. So much lower than we observe empirically. Now, if we apply the demographics projected for the year 2050 by the United Nations, where we have high life expectancy, low fertility, low population growth rate, meaning that the cohort of the retirees increases relative to the cohort of the workers, and we approach dependency ratios, old age dependency ratios of 50, 68, or in the case of Japan, of 80%, the optimal public pension system in our model is 0, to abolish public pension. So this exercise here that we conducted over the last 3 videos in a 2-period overlapping generations model, where we studied the effects of public pensions, pay-as-you-go pensions on equilibrium values, savings, and welfare, also carries over to large-scale overlapping generations model with income uncertainty, with more realistic modeling of the demographics. However, let me already mention to you, welfare effects will not be as large as we have computed here in table 6.4. So we will not have values of 30% or 40%, but more in the range of 1, 2, or 3% of total consumption. In order to get to this application on optimal pensions, what we do next in the next video is that we will introduce annual periods. So we will not have 2 periods. Young workers live 30 periods, work 30 periods, and old workers, they work 30 retire for 30 years. But we will consider annual periods, and then we can, of course, model the behavior much better and also can look at the demographics. For example, now we have many 50 and 60-year-old people, the baby boomers, and of course they behave different than people who are 20, who are 80. For example, the labor supply on average is a little bit lower than those of the 30-year-old, but on the other hand, they might have a higher savings rate. So this needs to be considered, and therefore in the next video we will look at the so-called Auerbach-Kotlikoff model, where we consider annual periods and are able to model the demography much closer.